Partitions of a set. Hello everyone. To begin today's lesson, let's first look back at what we have already covered. In our previous subsections, we explored the concepts of equivalence relations and equivalence classes. During those discussions, we discovered that an equivalence relation essentially acts as a tool to group elements of a set together, provided they share a specific common property. Now, the concept we are introducing today, the partition, is the logical conclusion of that grouping process. In simple terms, you can think of a partition as the way an equivalence relation slices or divides a set into several distinct, non-overlapping pieces. As we move forward in this lesson, we will define exactly how these divisions work and the specific conditions that must be met for a collection of subsets to be called a partition. Understanding the concept of a partition. Now that we have introduced the general idea of slicing a set, let us look at the formal definition. A partition of a set X is a collection of non-empty subsets of X, with the critical requirement that every single element of set X must belong to exactly one of these subsets. This means no element can be left out, and no element can be in two different subsets at once. In mathematical discussions, you will often hear these individual subsets referred to as the cells or blocks of the partition. You can think of these as the distinct pieces that make up the whole set. Connecting this back to our previous discussion on equivalence relations. Whenever we define an equivalence relation R on a set X, the resulting equivalence classes automatically form a partition of set X. Essentially, this means that the equivalence relation serves as the mechanism that divides the set X into several disjoint subsets. To ensure we fully understand how this works, we will now move to the next slide to examine the three fundamental conditions that must be satisfied for a collection to be considered a true partition. The three fundamental conditions. Now that we understand that an equivalence relation essentially slices a set into distinct pieces, let us examine the formal requirements for these pieces to be considered a true partition. For a collection of subsets to be officially recognized as a partition of set X, which is induced by an equivalence relation, three fundamental conditions must be strictly satisfied. First, let us look at condition 1, internal relation, also known as homogeneity. This means that every element within a single partition or equivalence class must be related to every other element in that same group. To put this in mathematical terms, if two elements, X and Y, belong to the same subset, then the ordered pair X and Y must belong to the relation R essentially. Everyone inside the group must share the same defining characteristic. Next, we have condition 2, external separation or heterogeneity. This is the opposite of the first condition. It states that no element in one partition can be related to any element in a different partition. Specifically, if X belongs to partition A and Y belongs to partition B, and partition A is not the same as partition B, then the ordered pair X and Y does not belong to the relation R. In simpler terms, the subsets must be mutually disjoint, meaning the intersection of set A and set B is the empty set. There can be no overlap between the groups. Finally, we have condition 3, completeness, also referred to as exhaustiveness. This ensures that no element is left behind. The union of all the partitions must equal the original set X. This means every single element of the set X must be placed into exactly one of the partitions. Mathematically, if our partitions are labeled as a sub 1, a sub 2, and so on up to a sub n, then the union of a sub 1, a sub 2, through a sub n must equal the original set X. Once these three conditions, homogeneity, heterogeneity, and exhaustiveness, are met, we have a perfect partition. To help you visualize how this works in a practical setting, let us move to the next slide and apply these rules to a real-world example involving a library. Real-world example, organizing a library. Now that we have covered the theoretical definitions and the three fundamental conditions, let us put these concepts into perspective with a real-world example. It is often easier to grasp abstract mathematical ideas when we apply them to a tangible scenario, such as organizing a library. Let us consider the following scenario. Imagine we have a set, which we will call set X, consisting of every single book in a library. To create a relation, which we will call relation R, we will use a simple rule. Book A is related to book B if and only if they belong to the same genre. To see how this works, we will follow a step-by-step breakdown. Step 1 is to verify that this is indeed an equivalence relation, as we discussed in our previous slides. First, the relation is reflexive because every book is naturally in the same genre as itself. Second, it is symmetric. If book A is the same genre as book B, then it must be true that book B is the same genre as book. Third, it is transitive. For example, if book A and book B are both science fiction, and book B and book C are also science fiction, then book A and book C are necessarily in the same genre. Because the relation is reflexive, symmetric, and transitive, we can confirm that relation R is an equivalence relation. Step 2 is to identify the partitions. The equivalence relation we just defined automatically partitions the library into subsets based on genre. For instance, subset A1 would contain all the science fiction books, subset A2 would contain all the history books, and subset A3 would contain all the biography books, and so on for every genre present in the library. Finally, in Step 3, let us apply the 3 fundamental conditions we learned in the previous slide to this example. First, the internal relation. Any 2 books within the science fiction subset are related to one another because they share the same genre. Second, external separation. A book in the science fiction subset cannot simultaneously be in the history subset. Therefore, a science fiction book is not related to a history book. This confirms that the subsets are mutually disjoint, meaning they do not overlap. Third, completeness. Every single book in the library must belong to at least one genre. If we combine all these genre subsets together, we recover the entire original set X, ensuring that no book is left out. This example demonstrates exactly how an equivalence relation slices a set into a partition. In the next slide, we will summarize the key takeaways to ensure these points are firmly understood before we discuss common mistakes. Key takeaways. Now that we have seen how this works with the library example, let us summarize the key takeaways to ensure you have a firm grasp of the concept before we move on. First, let's look at the relationship between equivalence and partitions. Essentially, every equivalence relation we define on a set X creates a unique partition of that set X. This means the rule we use to relate elements automatically determines how the set is divided. Second, we must remember that these are disjoint subsets. The subsets, which we have been calling equivalence classes, never overlap. In mathematical terms, this means their intersection is always the empty set, often denoted by the symbol emptyset. Just like in our library example, a book cannot be in 2 different genre-based partitions at the same time. Third is the principle of total coverage. The union of all these partitions must recover the original set X entirely. This ensures that the slicing of the set is complete and that no element is left out. Finally, we have mutual exclusivity. This simply means that any given element X belonging to set X must belong to one and only one equivalence class. There is no ambiguity. Every element has exactly one home. Keep these 4 points in mind, as they are the gold standard for a valid partition. In the next slide, we will discuss some common mistakes to avoid so you don't fall into these traps during your exams. Common mistakes. Now that we have covered the theory and a practical example, let us address some common mistakes to ensure you avoid these pitfalls when solving problems. First, let's discuss overlapping subsets. A frequent misconception among beginners is the idea that partitions can overlap. However, as we established earlier when discussing external separation, if 2 subsets share even a single element, they are no longer disjoint. Consequently, they cannot form a valid partition. Secondly, be careful not to ignore the rule regarding the empty set. It is important to remember that a partition must consist exclusively of non-empty subsets. In other words, you cannot include a subset that contains no elements as part of your collection. Thirdly, watch out for missing elements. A common error is creating subsets that fail to cover the entire set X, referring back to our condition of completeness. If even one single element of set X is left out of the subsets, the collection is not a partition. Finally, it is crucial not to confuse the relation with the partition itself. To put this in the context of our library example, the relation is the rule we use, such as the rule that two books must have the same genre, whereas the partition is the actual resulting group of sets, or the physical piles of books we have created based on that rule.